Hello, it's Keith here, and this is another YQuest series episode. We're going to be looking at the Atari 800 and 5200 today. Now, I ported my YQuest game, which was originally a Z80 game, but then became a 6502 game, and I ported it to both of these systems, and it's one common piece of code that runs on both, as I try to always make the case with my tutorials. Now, if we just have a look at this one here, you can see the game is basically the same as on all the other systems. I'm using the 4-color graphics mode here, you can see, and we're going to be looking at the code today, and we're going to learn what it took to get this game ported to these systems. Now, if you're not familiar with YQuest, you need to know that this is based on the simple series for these tutorials. It was that code, originally the Z80 code, but then I ported to 6502 and now the 68000. And it's that code that this is based on. So the idea of this is that if you are someone who's looking to make your own simple little game, this kind of proves that the code we looked at in the simple series is good enough to make some kind of game with, because we made that. Okay, so let's go over the code that makes up this one. Now, the code is called A52 for Apple 5200, but it's the same code that runs on the Apple 800 as well. There's just a few slight tweaks, and you can see there's compiler conditions here that will compile different symbols and things for that alternate version. Okay, so we're going to go over the code today. Now, the first thing we've got here is some definitions of the screen size for the common code, and then we've got some definitions of the collision masks. Now, because the resolution of some of the screens doesn't allow pixel level movement, usually doesn't, we sometimes have to remove some of the details of the calculations to make sure that what we're showing on the screen as overlapping is what we're calculating as overlapping. So that's what those do there. Then we've got a definition here that turns on 4-color mode. There is still some code relating to 2-color mode. The game doesn't really support it, but I've not taken anything out, so you can convert it to 2 colors if you prefer. Okay, we've then got some definitions of some 0-page entries here. We need some temporary variables and also some user RAM. Now, the game code needs some area of memory to actually store the variables of the game, things like the object positions and things like that. And then we got some symbols that are in different locations depending on the system. So on the Atari 800, those are in that position. On the 5200, they're in that position. And we're running from cartridge ROM in both cases, and the starting address is different. Now, the initialization here is just clearing out any old data, setting up the display list, turning on the screen, and now this is basically the same as with the simple series, although I think the display list is in a different memory position now within the ROM because I needed more ROM space, but other than that it's basically the same. Here we're clearing the game's temporary variables just to start a new game. Then we're setting the lives number, the level number, and restoring the player object, getting ready to start the game. Next, we're going to draw the title picture to the screen. Now, the title picture is here, and we're loading that into HL here. Then we're loading each byte of the title picture and drawing them to the tile map. So it's 1 byte per tile. We're calculating the address of the tiles in memory, and then we're multiplying up the XY position to a byte position. So 1 byte per tile horizontally and 8 lines per tile vertically here. And then we're using show sprite to show that to the screen. And we're repeating until the entire title screen has been drawn, and that's what makes that up there. Once we've drawn the graphics, we then show various text messages to the screen. You can see press fire, the high score, and the URL there. And then next, what we're doing here is we're waiting for the player to press fire before starting a level. This happens at actually every level, not just the first one. We wait for fire, clear the screen, center the player and give them some invincibility, and then we define the objects for that level, the enemies, the crystals, things like that. What we're doing next is we've got a delay loop, and we have a variable x which we're using to store any key presses. So we wait for the player, we see if they've pressed a key, and we store it in x if they have, ready for processing later. Now, once we've finished that loop, we're going to draw the on-screen UI, the pieces of text at the corners of the screen, and then we're going to blank the old sprite away from the player object. Now, the player object we store in 0-page entry IX, and the blank sprite routine will clear the old sprite off the screen by drawing a space in that position. Next, we're checking the timeout. You see, when you press up, down, left and right, you're increasing or decreasing the acceleration in that direction. Now, if you accelerate too fast, you'll quickly lose control. So when we press a key, the key timeout sets, and until that key timeout reaches 0, any further holding down of that key will be ignored. And that's what that's doing. Here's the key directions for up, down, left and right. What we do is we use IX pointing to the player object still, and an offset of Y pointing to the Y acceleration or the X acceleration, and we increase or decrease the acceleration according to the direction. If the fire button is pressed, we use the fire button routine, and the code does have the ability for a second fire button, though it's not supported on this system at the moment, and that would stop the player in their tracks if we were using that. Okay, finally we update the key timeout, then we handle all of the movements of the objects, the enemies and things like that, and that also handles collision detection and things. And we've just got another delay loop because this system was running a little bit too fast, it seems, so we're just slowing it down a little bit more there. And then we're jumping back to the top for another iteration of this loop here. Now that's all of the code for the main level loop. What comes next is the graphics routines and things like that. When we want to clear the screen, we're clearing memory address 2060 and onwards, and we're clearing 1F00 bytes of data in hexadecimal, and we use CLDIR, which is one of my common routine programs, which will just write zeros to that range. The print character routine uses the bitmap font. There's 8 bytes per character, no character before space, so that's calculating the offset within that font of the character we want to show. We're then multiplying up the X and Y position to an 8x8 tile, and we're using the show sprite routine to show it to the screen. The font, as it's stored in memory, is in the same format as the sprite data, so the font routine and the sprite routine are basically the same, which makes it a lot easier. Blank sprite here will check the collision program of the object that IX points to. If it's over 250, then that's a dead or uninitialized object, so we wouldn't want to do anything in that case. Otherwise, we draw a space using the font, removing the current object from the screen. Here's get sprite address. This calculates the address within our bitmap data of the current sprite passed by the accumulator. There's 8 bytes per sprite. There's also 4 banks of sprites, and so we're needing to multiply the sprite frame by 128 here, and adding that as an offset as well from the bitmap data, which makes up the 4 banks of sprites. DoGetSpriteObject uses IX as the source of the object, and this is what's mostly used during the game. You see all of the objects moving around the screen have a common definition of their attributes. There's the sprite, which is loaded in here, the X and Y position, and then the Y position just has the bottom 3 bits removed because we're moving in 8x8 strips just to keep the drawing routines nice and simple. So here's the show sprite routine. It's basically the same as we saw in the simple series. Now we're just calculating the screen position, and we're transferring 8 bytes to the screen, moving down by 1 line each time by adding hexadecimal 28 to do that. The get screen position routine is the same as when we saw it before here, so we're not going to go, that was in the simple series, so please take a look at that if you need to. Wait for fire routines here, use this read controls routine, which you can see just here, and these will calculate and see if the fire button's been pressed. It waits for the fire to be pressed and then released, so it's kind of a debouncing routine, and it re-randomizes the random number generator while that's being waited. Okay, the read controls routines here are basically the same as we looked at in the simple series. The only difference is we're now reading in the joystick as well. That was covered in the platform specific series before, so please take a look at those if you need more details of the joystick reading routines. The important thing to notice is they are different for the Atari 800 and 5200 because the hardware is physically different, so the way we have to read the joysticks is very different, unfortunately. Then we've got some common routines here that are just handling the multi-platform code, and we've got our font here and our 4 banks of bitmap data here. They're in the same format, and it's just basically in the same format as the screen. There's no compression or anything, obviously. The last thing here we've got is the display list. Now the display list has been moved to BF20. That's a little bit further down in the ROM than before, and that was just to make some extra space, but apart from that there's not really much changed here. And then the ROM footer here is common on all systems and has a pointer to the start of our program code up here. Now that's actually all of the platform specific code for this system. As I say, it's all basically based on the simple series, and the idea of this example of this YQuest game was to show that you can take a relatively simple example like the one in the simple series and turn it into a legitimate game if you can manage to sort of motivate yourself and plan your project through well enough. So hopefully this will be of some interest to you. Now the code for today's example is available to download on my website, as is the build script, of course, and I totally encourage you to download it and modify it and make something of your own of it. And if somehow you manage to make a commercial game with it and you're able to make some money of it, you don't need to give me credit or anything, you're totally welcome to do so. So as I say, hopefully it's of some use to you. Anyway, I hope you've enjoyed this. So YQuest is going to continue with a few other systems, and I will be doing similar games again in the future. So if you liked this kind of thing, if you like seeing a program being made and things, please like and subscribe, or follow on if you already are. But whatever you do, I hope you enjoyed this, and I wish you the best with your creative projects and programming. Thanks for watching today, and goodbye.